Hi, this is Arpan Gupta and today I will discuss about neural networks autoencoders. So we will be taking an example of MNIST data set and we will try to see how we can implement autoencoders in TensorFlow. So let's see an example of this simple neural network autoencoders. So autoencoders basically try to represent the complete data into lower dimensionality. So it kinds of encodes from higher dimensionality to lower dimensionality. And then later it has decoder functions which try to convert from the compressed state to the original state. So here we are discussing about the MNIST images, which is of the pixels 28 by 28. So since we are using a simple neural network encoder decoder scheme, it will be like we are squeezing the complete image into 28 by 28. So it will be 784 pixels, and you can just say that each image is squeezed into the form of dimensions having 1 by 784. So instead of feeding the 2D image, we are feeding the 1D vector into the neural network. So it will be 784 dimensions. So in terms of machine learning, we are actually we can think of each of the image as a single row having 784 columns. So basically autoencoder will what it will do is that it will try to encode each of the image, that is 784 pixels. It will try to convert into lower dimensionality, let's say 128 dimensions, and then it will try to decode it into the original state, which is 784. Basically the aim of using this autoencoder is to compress the data into lower dimensionality, so that we can use in other machine learning techniques also to encode the higher dimensionality into the lower dimensionality. There can be a number of use cases based on the actual data which we have. Here we are taking an example of images, so we can use this compressed state in different kinds of machine learning and deep learning stuff. So basically the aim of this tutorial will be to encode and decode using autoencoders. So first, let's say we have an image of 28 by 28. So we will be having 784 dimensions. Using this encoder decoder scheme, we will convert this 784 to 256 dimensions and then into 128 dimensions. So this 128 dimensions will be known as the compressed state. So where we are trying to compress it, each of the image of the dimension 784 into the 128 dimensions. So once it is encoded into 128, that means each of the image will be encoded into 128 dimensions. And once it is encoded into 128 dimensions, it will be decoded into the 784 dimensions. So basically we will try to see how accurate this compressed state will be. This state is also known as latent state or the compressed state. So now let's see the matrix multiplication which happens in basic neural network is like say we have a matrix of x by y dimension, that is number of rows being x and number of columns being y. You can multiply with the other matrix which has the dimensions of y by z, that is the number of rows will be y and the number of columns will be z. That means the most important thing in this is to keep in mind that the number of columns should be equal to the number of rows of the second matrix, and if you multiply these two matrices, you will get the result of a matrix which has the dimensions of x by z. So x will be the number of rows in the first matrix and z is the number of columns in the second matrix. So this is the basic matrix multiplication which you need to follow in this tutorial. So what we will do now is we have the images, and say we are feeding, we won't be feeding all the training images at in a one go. We will be feeding a certain number of images, say 200 or 256 or something like that. That is known as the batch size for the training. So let's say we are feeding the this batch size of something, let's say 256, and let's say the number of inputs. So we have already compressed the image into 28 by 28, that is 784. So the feeding dimension of to this neural network in TensorFlow will be batch size by number of inputs. So batch size will be whatever we are feeding it in the TensorFlow. That it can be 200 or it can be 300 depending on your choice. And then the number of units inputs will be 784, as we have compressed it into 28 by 28. So it will be 28 by 28 is 784. Now what we are doing is using the neural network encoder scheme. What we will try to do is convert this matrix into using the another weight matrix, which is which is a number of inputs and number of hidden layer h1. So it is like weight matrix w1, which will be of the dimension number of inputs, and the number of columns will be number of num underscore h1. Now we are using this weight matrix w1. So this is second one is w1, and the third one is w2, and fourth one is w3, and the first one is the inputs dimension. So that is the batch size comma the number of inputs, which is 784. So now we are actually going to use the matrix multiplication. Basic understanding is we have the input of batch size by number of inputs. So the weights of they should have dimensionality such that the number of rows in it should be the number of columns in the input. So since the number of columns in the input matrix is num underscore inputs, so number of rows should be num underscore inputs. So this is the weight matrix, first weight matrix. Now the second weight matrix is num underscore h1, because in the first weight matrix we have number of columns as num underscore h1. So you just have to focus on the second element of the matrix and the first element of the first dimension of the matrix. So if you see the second and third, so num underscore h1 should be equal to num underscore h1 here, and if you see third and fourth, so num underscore h2 should be equal to num underscore h2, and if you see fourth and fifth, you see num underscore h1 should be equal to num underscore h1. So this is very important to understand how we convert the dimensionality of the matrices till we reach at the point where we want to. And so if you see, so num underscore inputs are 784, then you convert into num underscore h1, that is 256, and then you convert into 128, which is num underscore h2, and then you again convert into num underscore h1, which is 256, and then you convert to num underscore inputs, which is 784. So it's like going from the input, using the encoder and converting into the compressed state, which is num underscore h1, num underscore h2, and then you are actually finally achieving the same image in the form of 784 pixels or rows. So it's like this: 784 converted into 256, converted into 128, and then again decoded to 256 and 784. So let's go to the coding section of this tutorial. So this is the GitHub profile of my so you can just see Arpan G87, and there you see the autoencoder with TensorFlow. Now what we are doing in this is we are just importing the libraries which are required for the TensorFlow and NumPy for this matrix and multiplication, and this we will be also using this matplotlib for plotting the images and the TensorFlow examples. So we are reading the data from the TensorFlow, which is already available in this. Once you have read the data, you see the num underscore inputs, which I have already explained, is 784 because we are squeezing the image into 28 by 28. Now num underscore h1 is 256, which you are compressing into from 784. You are compressing into 256, and then you are compressing into 128, and then again 256, and then 784. This is how you are trying to do the squeezing of the data. So we are actually we are just having the actual data which will be which will be fed as x with the tf dot placeholder float, and the shape is like the none is given for the batch size, which we don't know, which we will be defining during the session training, and num underscore inputs as 784. So we are not feeding the image as a 2D image, we are feeding the as each of the image as 784 column 784 dimensions. So each of the image will be 1 by 784. So if you have batch size or you have 10 images, so it will be 10 by 784 matrix. So if you have 100 images, it will be 100 by 784 data size. So you are just having your you are encoding as tf dot placeholder, and you are in TensorFlow you have to use the placeholder for encoding so that you can use it further. Now you have the batch size, which is the number of images which you want to use to train the model for in a single go, and you will be using the number of steps like 40,000 for the training, and the learning rate is the for the like the we have some algorithm for which we train, so how fast it should train, that is the learning rate, and the display step is after how many steps do you want to display the what is the cost function and what is the accuracy of the model, so that we can just keep track of how our model is going on. So basically, which I have already explained you, that we have two kinds of things in autoencoder. One is encoder and the other is decoder. Encoder is trying to convert the 784 into a compressed state, which is the compressed state, and then compressed state will be again converted into this decoder. So this is like the scheme of encoder decoder, and this is very simple. I have already explained how you do the matrix multiplication. You are using that tensor matrix multiplication using the TensorFlow, so you will be just tf.matmul, and if you want to add two things, you will be using the tf.add. And then if you want to do the sigmoid function, just use the submodule of nn inside the tf, which is tf.nn.sigmoid. So what you are doing is you're feeding the images as x, and then you're multiplying by w, and then adding the bias b1. Once you have done this, which is wx plus b, you are just converting, you are using the sigmoid function so that you can again convert into another dimensionality. So once you have L1, you use the matrix multiplication x and w1, which will be wx1, then you add b1, which is wx1 plus b, then you use the sigmoid function. After that, what you are doing is you take this input again and then convert with the another weight matrix, which is w2, add the bias, and then sigmoid function. So only thing which you need to keep in mind is the weight matrix dimensionality, which I have already explained. So this will be the encoder layer, and this is again the decoder layer, where you use the w3 and b3 and w4 and b4. Now the weight matrix, which I have already explained, is w1, w2, w3, w4, and b1, b2, b3, b4. You encode it as a df dot variable, and then you are using the random normal distribution of all the elements in this matrix. So now the weight matrix of initial where the w1 weight matrix should be of num underscore inputs comma num underscore h1, which I have already explained here. See, so input is batch size num underscore inputs, so the weight matrix should be having num underscore inputs as the number of rows, and then you can have any number of hidden layers, hidden units, you can say a number of hidden units. So num underscore inputs comma num underscore h1, then num underscore h1 to num underscore h2. This is how it is going on. So num underscore h1, then num underscore h2, then num underscore h2 to num underscore h1, and then num underscore h1 to num underscore inputs. In the B case, which is the biases, you need to just keep in mind that it is always equal to the second dimension of this matrix, which is num underscore h1, num underscore h2, num underscore h1, num underscore inputs. These are the dimensions. These are just single one dimensional vectors, and the weights are two dimensional matrices, which should be of the dimensionality which I have discussed just right now. Just keep in mind the number of rows in the second matrix should be equal to the number of columns of the first matrix. Given these weights and matrices, and given these encoder and decoder function, now you are ready to go for the training of the session. And just what you need to do is use this encoder layer function, feed the x, which is the input, and then just in the decoder function you feed the encoder layer encoder function, which is this one. This is the output. This is this output which you are giving to the decoder. And once you have done this, what you do is prediction will be the output of the decoder function, which is L2 here. So you will write predicted is equal to decoder underscore fun, which is here. Actual is, which is your inputting as a you have 784 pixels for each of the images. Now the cost function will be root mean square error, so which is like actual minus predicted square, and then you take the average. So you are using the tf dot reduce mean, and then tf dot pow is used for power. So actual minus predicted, you are using second power, which is like x minus y whole square, and then you take the mean. Now you are using the RMS prop optimizer, which is similar to gradient descent optimizer, and there are lots of other Adam optimizer and all those. So we are right now using RMS prop optimizer, and the learning rate is, which is you have already given above. You can change it according to your convenience, and then you use the training is optim dot minimize, which is this function optim, and you are trying to minimize the cost function. So using this algorithm RMS prop optimizer, you are trying to minimize this cost function, which is the RMSE between the actual and the predicted. Now this is what we need, the cost function and the training. So we are just defining, we are initializing all the variables. So we just tf dot global variable and initializer, and now you just write the simple code for getting this loss and at each step. And what you get at the end is, these are the real images and these are the compressed state images. We can see that this autoencoder has done a very good job in compressing all these images into a state which is like 128 pixels, and 128 pixel, that means 784 has been converted into 128, and still we have very less noise, and we can just use this compressed state for other machine learning approaches or deep learning approaches or other tasks. But what we are doing in this session, just I will go through a little bit, and with tf.session as says.run, initializing you are the global variables, and then for each step you're going from 1 to number of steps, which is 40,000. You are taking the batch, and you are not taking the y because you don't need the y. You're just compressing the original image into the compressed state and then decoding. That's why we are not using the batch underscore y. So bdf.train.next batch is batch size, which is batch size is fixed, which is 256. And then you are running the session, which is sys.run training. Training is like this optim.minimize cost function. You're feeding the dictionary, you are feeding only the x because you don't need the y, because you're just compressing x into compressed state and then again into x. So, and this part of code is just to display. If step is divisible by display step or it is 1, you will see the loss. Loss is the cost function, which is you have defined here. The loss says.run cost function and training. You're feeding the dictionary, which is x. So here you are calculating the list of these two things, which is one, first is cost function, and the second is training, which is the optim.minimize, minimizing the cost function. So you will keep track of both, but you don't need the second one. You just want to see the cost function. That's why we are just writing loss for the cost function, just printing the loss at each of the step, at each of the display step, and then you will see what is going on here. The first step, you see the loss is this, and second 1000th step the loss is 0.13, and finally you see this loss is pretty low, that is cost function loss is very low. Now this part of code is for displaying the images in the real and compressed state. What we are using is, you're again taking the batch of the test images, not the training images, and then you're running this session sys.run, and you're using the decoder function which you have already defined here, and you're using the feed underscore dictionary, which is the batch X, which is this one. And now your original images you are actually reshaping is batch X, and you are reshaping 28 by 28, because we were having in 784 dimensionality, so we need to convert into 28 by 28 in order to see the images. So, and this canvas we have created because we are not having just one image, we are having 4 by 4. So we have a canvas of 4 by 4, and each of this element is one image. So that's why we are using this I and J for in the loops. And the reconstructed images is this one, where we are using the G is this session. You are running the decoder function for the test image. So output of the decoder function will be for the test image, and the output of the decoder will be the predicted thing, which is here we are using predicted is equal to decoder underscore fun, and this decoder underscore fun is which we are using for the test images instead of the training images. That's why we are saying reconstructed images. Now you're just seeing the images are pretty nice, and in the reconstructed steps also images, they are quite recognizable, so there is very less noise. So if you do training for a longer time or for better parameters, you can have better parameters, I mean to say, you can have more number of layers with different this weights, W1, W2, W3, W4. You can use n number of layers depending on that. Instead of using the simple encoder decoder neural network layer, you can also use the convolution neural network for autoencoders that I will be discussing in the later videos. So if you have liked this video, please do not forget to like and subscribe, and if you do have any comments or if you have any questions, you can just comment it out. So thanks for watching this video. Bye bye.